In this video, we are going to learn how to detect deadlocks. To begin with, we are now going to look into a resource allocation graph. I hope all of you know what is meant by a resource allocation graph and how to draw one. Now, the question before us is how to detect deadlock using a resource allocation graph. Let me now show you a resource allocation graph. Now, if you look at this graph, what do you observe from this graph? We can observe that we have squares symbols as well as we have got circled symbols. Now, wherever we want to represent a process, we'll have to use the circles. And whenever we want to represent a resource, then we use a square. Now, if you look at this graph carefully, we observe that there are 5 processes, P1, P2, P3, P4, and P5. And we have 5 resource types, R1, R2, R3, R4, and R5. Now, if you look at the resource type diagram very carefully, you can see a single square. It's an empty square. The name of the resource type is written outside. Whereas if you look at a process, you find that the name of the process is written within the circle. Now, the reason why the name of the resource is written outside the square is that this represents a single instance of a resource type. That is, if I take R1, R1 could be a resource type. For example, it could be a magnetic tape, a magnetic disc, a flip-flop, or a CD or a DVD. So that is the type of resource. And this empty square represents that there is only one unit of that particular resource type. And what we are going to see in this video is we are going to learn how to detect deadlocks using a resource allocation graph, wherein we are only going to consider single instances of a resource type. So that is why all the resource types which are drawn here are with empty square boxes. You don't have anything written within the box. Suppose I want to represent a resource type with multiple instances, then I will put that number of instances as dotted circles within the square. So now in this video, we are only going to concentrate on single instance of a resource type. So I hope you're able to understand. That is, I hope you're able to read this particular resource graph. Now, how do we detect deadlocks using such kind of a graph? What we have to do is, from this resource allocation graph, we have to construct what is called as a wait for graph. So we are now going to construct what is called as a wait for graph. Now let's learn the construction of the wait for graph. Now let me now start constructing the wait for graph. Now what should we do initially? Now this is our resource allocation graph which is given to us. Now the first step that you need to do when you are drawing your wait for graph is, in your wait for graph, mark the processes alone. That is, mark P1, P2, P3, P4 and P5 as shown in this diagram here. This is my wait for graph. I have marked only the processes in my wait for graph initially. So this is my step 1. Now, the next step is start from each process. That is, let's start from P1 and find out what P1 is requesting for or what P1 is holding. Now, if you look at this resource allocation, look at the resource allocation graph given here. Now, if you observe the graph, P1 is requesting for R1. This edge which moves from P1 to R1 is called as a request edge. So P1 is requesting for R1. And what is this edge called as? This is the assignment edge, allocated edge. That is, R2 is being held by P1. That is the meaning. So now I am going to only show the request edges in my wait for graph. So if with respect to P1, what is P1 waiting for? P1 is actually requesting R1. This R1 is being held by whom? R1 is being held by P2. Therefore, what we do is, we are actually going to draw the wait for graph by drawing an edge between P1 and P2. That is, my wait for graph now becomes like this. What does this mean? This means this arrow from P1 to P2 means P1 is requesting for a resource which is being held by P2. This is what is meant by P1 to P2 arrow. That is, P1 is waiting for P2 to release the resource R1. So like this, with respect to every process, I have to fill my wait for graph. So now I am done with P1. Let's now move to P2. With respect to P2, what do you observe? Now P2 is waiting for which processes? Look at the graph, resource allocation graph, and then let's find out. P2 is requesting R3 held by P5. That means I must draw an edge from P2 to P5. P2 is waiting for P5. Similarly, P2 is requesting for R4 held by P3. That is, P2 is waiting for P3. And P2 is requesting for R5, which is held by P4. Therefore, P2 is waiting for P4. So now, in my wait for graph, I must draw 3 arrows proceeding from P2 to P5, P2 to P3, P2 to P4. Now look at the wait for graph. This is how it has changed. Now I have completed P1 and P2. Let me now proceed to the third process, P3. Now look at P3 in the resource allocation graph. P3 is requesting for R5, which is held by P4. So I should draw an arrow from P3 to P4. Okay, now from P3, I do not have any other request edge. So my graph is just going to be an arrow from P3 to P4, meaning P3 is waiting for P4. So now I add that edge and my graph is now changed. So look at the graph now. It has changed like this. So I'm done with P3. Now I move to P4. Now what is P4 actually requesting for? P4 is requesting for R2 held by P1. And P4 is not requesting for anything. Therefore, P4 is actually waiting for P1, which means I must draw an arrow from P4 to P1. So let me see how the arrow is added. Yes, now P4 is waiting for P1. Now I move on to the last process, P5. From P5, I do not have any request edge. Hence, my wait for graph will not change. My wait for graph is going to be the same. So I'm done with the conversion of the resource allocation graph into the wait for graph. So the resource allocation graph has now been converted into the wait for graph. So this is our final diagram that we get. Now, what should we do here? The thing that we have to do here is you have to check for cycle formation in the wait for graph. Find out whether there's any kind of a cycle formed in the wait for graph. See, if you observe carefully in the wait for graph, you have a cycle formation between P1, P2, P3, P4, and P1. So you start from P1, that is P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, and P4 is again waiting for P1. So this is a cycle formation. Find out whether there is any other cycle being formed. Yes, P1, P2, P4, and P1. And then again, look at this P2, P3, P4, but this is not from P4 to P2, it is from P2 to P4. So this is not a cycle formation. Hence, I have two cycles being formed, P1, P2, P3, P4, P1, and then P1, P2, P4, P1. So I have to check in my wait for graph whether there are any cycle formations. And if there are cycles, that means there is a deadlock in my system. So your conclusion will be, if you are going to detect a deadlock in a resource allocation graph, after you convert it to wait for graph, check for cycle formation. If there is any cycle formation, then you can conclude that there is a deadlock in the system available. And which are the deadlock processes? All the processes which are involved in the cycle formation will be the deadlock processes. So my first step, I said, after drawing the wait for graph, is you check for cycle formation in the wait for graph. If you do not have any cycle formation, then you can declare that there is no deadlock. But here I have a cycle being formed, P1, P2, P3, P4, P1. So these are all the processes which are in the deadlock. This is how you detect deadlocks using a resource allocation graph. I hope it was very clear to you. Let's meet in the next video. Thank you.